Thank you, everyone. It's my honor to present our work titled Software Visualization and Deep Transfer Learning for Effective Software Defect Prediction. My name is Chen Jingying from Zhejiang University of Technology, Hangzhou, China. I will introduce our work from 5 aspects. Why we choose this topic? Because we want to bridge the gap between deep learning and defect prediction without utilizing feature extraction tools. Then we will explain how the deep transfer learning works for the defect prediction efficiently, both in theory and experiments. Finally, we will conclude the work and point out some future directions. As we all know, most prediction methods build prediction models based on modules in the source code and historical development data at different levels of modeling. We wondered if we can tell that those two programs are different when we visualized them. From the observation of the above two images, both semantic and structural similarities between two programs can be effectively identified by visually comparing program images. From the surprising observation, we prepare to use an end-to-end deep learning model as our basic method. First of all, we convert the files into images and use the deep model to automatically accomplish the features extraction and complication. Two extra strategies, transfer learning and self-attention mechanisms, are designed to improve the prediction performance, benefit from the domain adaptation capacity of transfer learning. Cross-project defect prediction has achieved promising accuracy, scored as the state of art. The overall framework of our approach, deep transfer learning for predict, is shown in the figure. It is comprised of 2 stages. The first is the source code visualization, and the second is modeling with DTL, which is short for deep transfer learning. In the first stage, we use a visualization method to convert program files into images. In the second stage, we built a DTL model based on AlexNet with transfer learning and a self-attention mechanism to construct an end-to-end defect prediction framework. We use that framework to predict if a new instance file will be defected or not. Here is the slide for the source code visualization. We call this progress most important because if the image can achieve a good quality, each source file is converted into a vector of 8-bit unsigned integers corresponding to the ASCII decimal. Generate an image from the vector. We qualify the file size with the image size. After several times of experiments, we conclude that their relation shown in the table, which is convenient for other researchers. We also model the basic method with deep transfer learning. Different from the original DAN model, we apply attention layer combined with the loss, MMD loss, distance loss, and also the cross entropy loss. Besides, we also analyze the model sensitivity to parameter choices. There are 3 critical parameters that are closely related to the model. From the simulation results, we find out that the loss limitation is sensitive to the model performance. The RGB permutation selection has less impact on the performance, and the proper image size is necessary. In the experiments part, we adopted 4 baselines each for both within project defect prediction and also the cross-project defect prediction in metrics of F measure. The first research question is, how does the deep transfer learning defect prediction compare to feature-based machine learning methods and AST-based deep learning methods in WPDP? We studied the T-SNE mapping of different methods for WPDP and conclude that the proposed DTLDP is effective and it could improve the performance of WPDP tasks. Like other deep learners, it is sensitive to small file sizes and also the unbalanced data. We also concentrate on the second research question: how does DTL-DP compare to feature-based machine learning and also AST-based learning methods in cross-project defect prediction? The conclusion is that the proposed DTL-DP shows significant improvements on the state-of-art in cross-project defect prediction. And we also did some case studies on the specific projects. And the third research question is, how much does each of the three mechanisms, for example, the data augmentation, transfer learning, and self-attention mechanism, contribute to our methods, contributes to the performance? The three mechanisms all contribute a lot toward the accuracy of our proposed end-to-end framework, both in WPDP and CPDP. Specifically, self-attention has the greatest contribution to WPDP, and transfer learning contributes the most to CPDP. We also calculate the time cost and analyze the time spending on the three strategies. Finally, we calculate the three parts and compare them each in different projects. There are also threats to the validity, threats to the internal validity and external threat. We analyzed both of them. After that, we conclude the work and experiments. We can conclude that our proposed method can effectively applied directly for most of the defect prediction tasks. And in the future, we will keep on digging the work of defect prediction in aspects such as negative transfer and imbalanced data sets. That's all my presentation. Thank you very much.